Welcome back to Low-Level Programming Crashcasts. I'm Sheila, and as always, I'm joined by my co-host, Victor. Before we dive in, I'd like to remind our listeners to rate our podcast on whatever platform you're listening from. Your feedback helps us improve and reach more programming enthusiasts.
Thanks, Sheila. Today we're continuing our journey through number systems and data representation. We've covered binary, decimal, and hexadecimal systems, as well as signed and unsigned numbers. Now we're diving into the fascinating world of floating point representation.
That's right, Victor. And to kick things off, I've got a quiz question for our listeners. Here it is. In a typical computer system, what's the result of 0.1 plus 0.2? Is it exactly 0.3 or something else? Take a moment to think about it, and we'll reveal the answer later in the episode.
Ooh, that's an intriguing question, Sheila. It seems straightforward at first glance, but it touches on some fundamental aspects of how computers handle decimal numbers. I'm excited to see how many of our listeners can guess the correct answer.
Before we get into the nitty-gritty, let's define some key terms. Victor, could you explain what we mean by floating point in computer science?
Certainly. In computer science, floating point refers to a method of representing real numbers that can have fractional parts. It's called floating point because the decimal point can float to any position relative to the significant digits of the number. This is similar to scientific notation in mathematics, where we represent numbers like 1.23 times 10 to the power of 4.
That's a great explanation, Victor. Now, I understand that the most common standard for floating point representation is IEEE 754. Could you tell us a bit about its history and why it was created?
Absolutely. The IEEE 754 standard was first established in 1985 to address the problem of inconsistent floating point implementations across different computer systems. Before this standard, each hardware manufacturer had their own way of representing floating point numbers, which led to portability issues and inconsistent results. The standard aimed to ensure that floating point arithmetic would produce the same results across different platforms, making it easier to write portable numerical software.
That's fascinating. So, how exactly does the IEEE 754 standard represent floating point numbers? I've heard something about signs, exponents, and mantissas, but I'm not entirely sure how they work together.
Great question, Sheila. The IEEE 754 standard indeed uses three components to represent a floating point number: the sign, the exponent, and the mantissa, also called the significand. Let me break it down. 1. The sign bit determines whether the number is positive or negative. 2. The exponent represents the power of 2 that the mantissa is multiplied by. 3. The mantissa represents the significant digits of the number. Think of it like scientific notation, but in binary. For example, in the 32-bit single precision format, you have 1 bit for the sign, 8 bits for the exponent, and 23 bits for the mantissa.
That makes sense, Victor. But how does this representation handle very large or very small numbers?
Excellent point, Sheila. The IEEE 754 standard includes special representations for extreme values. For instance, it has representations for positive and negative infinity, which are used when a number is too large to be represented in the available bits. It also has a special representation for not a number, n, which is used for undefined results like 0 divided by 0 or the square root of a negative number.
Wow, that's quite clever. But I'm curious, are there any limitations or challenges with this system?
Absolutely. And this brings us to one of the most important aspects of floating point representation: precision. Because we're using a fixed number of bits to represent an infinite range of real numbers, we can't represent all numbers exactly. This leads to rounding errors in calculations, which can accumulate in complex computations.
That's really interesting, Victor. Could you give us an example of how these precision issues might manifest in real-world applications?
Sure thing, Sheila. A famous example is the Patriot missile failure during the Gulf War in 1991. The system's computer was using floating point arithmetic to keep track of time, and small rounding errors accumulated over the course of 100 hours of continuous operation. This led to a targeting error that resulted in a failed interception. This incident highlights the importance of understanding floating point precision in critical systems.
That's a sobering example, Victor. It really drives home the importance of understanding these low-level details. Now, I remember you mentioning something about normalized and denormalized numbers earlier. Could you explain what those are?
Certainly, Sheila. In the IEEE 754 standard, most numbers are stored in a normalized form, where the most significant bit of the mantissa is always 1. This bit is implicit and not actually stored, giving us an extra bit of precision. However, for very small numbers close to 0, we use denormalized or subnormal numbers. These allow us to represent numbers smaller than what we could with normalized numbers, at the cost of some precision.
I see, Victor. That's a clever way to extend the range of representable numbers. Now, I think it's time to reveal the answer to our quiz question. Remember, we asked what the result of 0.1 plus 0.2 would be in a typical computer system. Victor, would you like to do the honors?
Of course, Sheila. The answer might surprise some of our listeners. In most floating point systems, 0.1 plus 0.2 does not equal exactly 0.3. Instead, you typically get a value very close to 0.3, like 0.3004. This is because neither 0.1 nor 0.2 can be represented exactly in binary floating point, leading to small rounding errors that become visible in the sum.
That's mind-blowing, Victor. It really illustrates the importance of understanding floating point arithmetic when working on numerical software. To wrap up, could you give us a quick summary of the main points we've covered today?
Absolutely, Sheila. Here are the key takeaways. 1. Floating point representation allows computers to work with a wide range of real numbers. 2. The IEEE 754 standard defines how floating point numbers are stored and manipulated. 3. Floating point numbers consist of a sign, exponent, and mantissa. 4. There are special representations for infinity and not a number, NaN. 5. Floating point arithmetic can lead to precision issues and rounding errors. 6. Understanding these concepts is crucial for developing accurate numerical software.
Thank you, Victor. That's a great summary. And to our listeners, we hope you found this deep dive into floating point representation informative and engaging. If you did, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us continue creating in-depth content on low-level programming concepts. Until next time, happy coding.